thank you so much for being on time. Thanks for the commitment, showing up on second day. I know it's spring break. Thanks to our students and our sponsors, our speakers. And today we have a very important two topics. We'll be more toward the technical expertise in extrusion. So Dr. Ubbink will be talking about the engineering, scaling up, and troubleshooting of plant protein extrusion for 1.5 hours. As we did yesterday, he's going to be quite technical, but I'll try to simplify it and maybe if you have questions, like more on the food science level, I will be more than happy to follow it up when we have the break. And with no further delay.
And me as well.
Yes, of course. Yes. Without any delay, I present Dr. Ubbink for the second time. Thank you.
Yeah, good morning. Thank you. Good to see you all. Great to have the courage for another full day of theory, applications, and lab-based work. So actually, when we were developing the format for this workshop, I thought it was done after my first lecture, but then Bilal had the brilliant idea. Says, you know, actually he had the idea, just wrote it in the program. Says, I want me to talk about scaling and troubleshooting. Scaling and troubleshooting. If I talk about scaling and troubleshooting, I also need to talk about engineering. So we need to introduce at least a couple of engineering concepts. So try to keep it as simple as possible, but I think some kind of, at least a conceptual understanding, and maybe for one of the parameters, an ability to actually calculate them and monitor them during your extrusion process is actually a really good idea. And I hope to convince you, during this session that it actually really worth the effort. I worked with many students and researchers over the past, with extrusion at least the past 12 years. I haven't had anyone who says, yes, let's focus on these parameters. At the end, I think they have all come to appreciate the importance of some of these parameters and really controlling and monitoring your extrusion process. The thing is also, scaling is, to some extent, it's a combination of science, engineering, and an art. Maybe even a dark art almost. So there's no one single solution. There's not going to be a closed, challenge that you can solve and there's one answer coming out of it. So my purpose is not that you run into your next experimental series and your manager asks you to scale it to production. They say, sure, I know it. I attended the lecture and I know how to scale it. No, that's not going to be the purpose of this lecture. Scaling is really tricky. There are these engineering principles at the foundation, but it also requires a lot of really hands-on understanding of the process. And there's a lot of, with those who are involved on a routine basis with scaling and extrusion, there's a lot of that expert know-how how to scale it. There are these rules of thumbs, some of them based on engineering principles. But there's also a lot of the know-how. And know-how often actually will give the right answer, or bring you where you think, hey, this looks like a properly scaled up process with a product which comes out, which is sufficiently consistent with what we're producing on smaller scales. But it's not perfect science. So also in those who are dealing, on a day-to-day basis with scaling, there's always a little bit of that magic in it from, is it going to work, is it not going to work? But my purpose today is that you have a little bit of a feeling maybe for the opportunities and the limits of scaling and maybe how some of those engineers, mainly process engineers dealing with it, how they go about. And maybe have a few words in their language we can actually communicate with. Because if you're working in R&D, and if you're working and maybe running your own pilot scale extruder and you develop prototypes or explore the behavior of some ingredients, you'll gain some expertise and insights in those systems. But then I think a really good way to work together is actually to work with someone who's really doing the scaling. But that you know where they're heading to, that you have maybe a bit of an idea what the limitations are. Then Bilal put also troubleshooting. So thank you, Bilal, because this is basically opening another box of Pandora and even less well controlled, because troubleshooting could imply anything that goes wrong. From something from the feeder to the dehydration of ingredients to when I'm running the extruder and suddenly the pressure shoots up and so on. So basically there's an unlimited number of cases I could bring up. Actually, I'll bring up in a little bit of detail one case which we see quite often happening in high moisture extrusion. That's the pulsating of the extruder, which gives rise to, if you extrude that ribbon, we saw that in the video yesterday, we saw that in the demo upstairs, that ribbon, if you can have a homogeneous texture, but also sometimes you see sometimes variation, almost, let's say you have a couple of inches has this texture, then a couple of inches is a little bit different. So we'll discuss as the one example there, as for troubleshooting, what can you do a little bit to mitigate these effects? But it's just one case, there are dozens, so I can have a list at the end and we can go over a few and openly discuss them. And also if you have situations, definitely bring them up and we can actually have a conversation. Troubleshooting and extrusion is basically unlimited what you can do, but I think let's take one case there. So let's get started. I'll initially have a few slides, actually branch it, link it from my lecture from yesterday to today's lecture. Talk a little bit about how to set up, how to design your extrusion process or how to set up your trials. How I do it and what I've found also to be useful in doing extrusion for a wide variety of products also of during my industrial career. Then we go to these engineering aspects, introduce a few concepts there, and we're going to calculate a few aspects there, and we're going to do one little simulation. We talked about the screws yesterday, and a little bit about the screw design and these elements. Today we're going to, as well as I'm able to manipulate it on the screen here, we're going to build a screw together. You're going to tell me which elements to put where, and we'll see if that, if we're able, with that screw that we design collectively, if we guess we're able to really convert a plant protein into an extruded product. We can still decide if we want to do high or low moisture extrusion, doesn't matter too much, but if we can really design a screw configuration using some understanding of what various screw elements are doing in that setup, in that profile. Then we go into the scaling aspects. We need some engineering principles there, but I also want to outline the limits of some of these engineering principles. And at the end, as I mentioned, a little bit on the troubleshooting. So let's go first in the design, do a little bit of recap from yesterday. So we're talking here plant protein extrusion. We talked about the extruder as the centerpiece of equipment in that whole complex setup. So without extruder we can't extrude, but actually without all these spheroferals we also can't extrude. These extruders were two types, single screw and twin screw. Which ones do we use for which type of processes? For a single screw extruder, where can we use that for plant protein extrusion? Low moisture extrusion, which is expanded extrusion cooked products. Twin screw extruder, for what products do we use that? For plant protein extrusion. High moisture, yes. Why? It's actually, we also use it actually for low moisture extrusion because actually, so these twin screw setup we can use for both the low moisture and the high moisture systems. The single screw extruder we can't use for high moisture system. The thing is, the material is so hydrated, we can't really transport it over that one screw with passive transport. The twin screw extruder, we have these intermeshing screws, and there we can have active transport. One screw basically cleans the other one, and the other one cleans the first one again. So we have that active transport over material in that extruder barrel, which is pretty low viscosity. It's about, let's say, at that temperature, let's say the consistency of a thickish peanut butter or something like that. So we need something to actively, peanut butter, doesn't really transport very well. You need to have something to really help that move along in that barrel. So very good single screw, twin screw extruder, yes?
What is the highest moisture that we can still extrude? Water content at 60%, 70%? What's
For a
the
twin screw
limit
extruder?
with a
Yes.
twin extruder?
Now Bilal asks here into a very interesting project we were running. We had a company actually reaching out to see if they could extrude egg. What is the water content of egg? What's the solid content in egg? So mixed liquid, you know, the yolk and the egg white. What's the solid content in egg? I think 17% or something like that. So let's say round it up 20%. So it's 80% water. I don't know why they wanted to extrude. I think everybody wants it. I think they want now even to extrude cheese. So I think extrusion is really cool technology. I don't think you need to extrude everything. But so can we extrude egg? Yes, we could. We could extrude egg on a twin screw extruder. I must say, it was challenging. But we love challenges, so we combine it with the real logic.
The wrong extruder.
No, it works. Yeah, so we really have to look at how the viscosity builds up. A long story short, you have to really carefully look at how the extruder builds up to make this, that the egg sets exactly at the die. Because what happens if the egg sets in the extruder barrel? What are you making?
Scrambled eggs.
Scrambled eggs, exactly. So yes, the extruder could be a really good technology to make scrambled eggs, but it's probably the most expensive way to make scrambled eggs. So yes, you can extrude up to these water contents, but that was more of a, from my side, I thought it was just cool to once try it and actually demonstrate the potential feasibility. Feasibility just on doing a lab, it never goes to production, but we could extrude, we could control that, we could extrude at 80 water content. But for actual practical means, in regular twin screw extrusion, for plant proteins, I think 60-65% is probably going to be pretty close to the upper limit. If you may be very careful and maybe have some additional hydrocolloids which bind water very effectively, maybe you could push it to 70%. But there you basically are you know, you plateau somewhere where you can do feasible twin screw extrusion. So as we mentioned yesterday, what typical water content do we use in high moisture extrusion?
40 to 60.
Sorry?
40 to 60.
40 to 60, yes, it's typically in that range around 50% water content. And that tip, yes?
So for the eggs, is that because after heating it will kind of like gel up? Is that a reason why it can be extruded at that high moisture?
So with the egg, there's two things. First of all, if the egg, you know, if you cook it, actually you know, it sets irreversibly.
Yeah.
So if it sets irreversibly and then you start, you know, mixing it, you get, you know, scrambled eggs. So you need to have it set really at the die, and at the die a little bit of pressure builds up, and then you have a really runny material. And if you don't take care, you get backflow of the egg in your extruder. Because there's very little grip of these flanges on the helices on the screws to actually push it forward. It is a bit of a clearance between the screw and the barrel itself. So if you don't take care, you can actually get some backflow of your material. So you need something with some kind of a little bit of a body that it actually will not show the backflow, but rather transport forward. But we're able to actually move it forward in the extruder. But then you build up the pressure at the die because there the egg sets. And then you need to be able to push it, but with a very runny material, it's very difficult to get enough pressure to push that egg then out of the die. So the die might block up with scrambled egg, which then get overcooked. And then basically then you can of course try to clean it a little bit, but that's the issue. So that's really the limit where it can go to. But typically for any practical feasibility, I think 60-65%, maybe occasionally 70%, there you're going to stop out unless you have very unique ingredient properties. Yeah? So we have a matrix premix. We can run it either over a feeder or we can act the feeder into this preconditioner. What was this preconditioner doing? Hydrating and mixing, yes. A mixing of what? Is it it's the mixing of the water in it. So I like your hydrating very much. So it's the mixing of water in the ingredient, and then that further hydrates the individual ingredient particles. And what's the second thing? Well, do we use water in the preconditioner, or what do we use in the preconditioner? Steam. So what happens? We're hydrating it, very good. Sorry?
Kind of pre-cooking it.
Pre-cooking it, so we're heating it up, so we pre-cook it. So with the starch, we can pre-gelatinize the starches. With the proteins, we can either denature them or soften them up already. We don't want to do it fully because it gets really sticky at some moment, but we can already condition it, actually pre-cook to some extent and hydrate and heat up these products before we feed them in the extruder. Then in the extruder, what are we doing in the extruder? Shear it, yes, we heat it, we first transport it, we heat it up further. And if the material is sufficiently cooked, so fully gelatinized or fully denatured or softened in case of proteins, we shear it. So we'll have a look, we'll have some special elements in the screw, but we'll have a look at the screw design that we see actually how can we most effectively shear it. Then we extrude it here. The temperature conditions could vary a little bit. We'll come to that. Then we have the low moisture extrusion versus the high moisture extrusion. What are the main differences between low and high moisture extrusion? What's the difference in setup of the extruder? Sorry? For low moisture, we can do it with a single screw, we can do it with a twin screw. But then we come at the end, so we have here the die. What? Sorry?
Cooling die.
For what type of products do we use the cooling die? High moisture extrusion. How does a cooling die look like?
It's like a brick.
It's a brick, and what is in that brick?
It's just a chamber with water.
It's cooling mantle, yes. And what are we cooling?
Material.
The material. Where's that material?
Where is it? It's
There's a slit. There's a long slit. We usually make it rectangular, a long slit in that cooling channel. So we extrude that material, that denatured, that sheared protein. We force it into that cooling channel. Yes.
It's a bit a tricky question. Flavors so sensitive to shear and heat. Could I inject my flavors in the last stage in the cooling die when it's exiting from the extruder? So I have the hot melt, I inject my flavors
In the cooling die.
between the cooling die and the heating die. So when they just
Here.
leaving the
Yes.
extruder, going to the cooling die, can I inject when I have the hot melt and I have more stability of
Yeah.
my flavor?
Yeah, it's not yes, actually I've been doing a lot of that work, not for meat analogs, but for actually making encapsulation system based on starch. So you can definitely, we can actually do that in the screw simulation. We can actually set it up. So what you can do here is actually, you can have here a port to inject water. You can here create a screw design that you can inject an oil or a flavor. So, and then you can mix that in. So you can do that just before the die, but you still have to do that in the extruder barrel, because then you can mix it, you can disperse it in that matrix. So yes, that's very well possible, and I've done it extensively, especially for controlled release systems which are based on starch, where you do a flavor or an oil, or actually I had a very nice project with Brazil some years ago where we're encapsulating it was thyme oil, an essential oil, which actually is very effective at killing mosquito larvae. And then you have a controlled release system with that oil, and you can put it in little water cups and containers everywhere. So in the rainy season, that actually it releases the thyme essential oil very effectively. It really kills the mosquito and has a really long shelf life. Yes, so you can, but if you inject that over here. Yeah? Good. So then we extrude, so we have high moisture extrusion, that's with that cooling die. In that cooling die, that protein, so we shear it, so there's a phase separation between the protein and the water. Then we stretch that in these lamella, and it sets in that structure that you saw yesterday. You have all been seeing the extruder. You have also played with the materials. Low marsh extrusion, how does that look like? How does the die look like?
We won't see it today, but
Yeah, yeah. You'll do low marsh extrusion, TVP extrusion today. It's simply a hole. It's basically a die plate which you screw or bolt on your extruder, and there's one more holes, and the holes can have can be just a circular hole. That's what's typically used in research. You can have also these intricate shapes. We seen yesterday that little video of these pasta, things shaped when they come out. Of course, you have to create a structure, but simply it's a metal plate with a hole in the simplest form. So we extrude that protein mass, high temperature, fairly low water content, but high temperature, with high pressure through that hole. What happens?
Cools.
It cools, yes. Does it cool? Is that the first thing that happens? What is the first thing that happens? It expands. Why does it expand? What is driving that expansion? Water. In which state? Steam, yes. So because it's a really high pressure just before it exits the extruder barrel, it's just overheated steam. And the pressure drop less than 40 or 50 bars down to 1 bar atmospheric pressure, whoop, there it goes. The steam flashes off, cooling the product. And of course the product also cools by itself, but there's a lot of evaporative cooling. So the product expands, the product cools. What happens with that structure, that expanded structure? What happens? Is it collapsing again? Is it setting? It's setting. So because it cools down, so viscosity goes up, water evaporates, viscosity goes up, so we get that expansion. It's more and more difficult. At some moment, basically the viscosity is so high that the structure sets. We cut it at that moment, and this thing drops down into a big container, continues to cool down, continues to evaporate water, and then we add in a product which is, if we would, the texture, what is the texture of that product? Crunchy. So I have a dry, crunchy product, water content below 10%. It's in what we call, we don't do the material science here, it's what we call the glassy state. So we have a stable, dehydrated product, which you can store for a long period of time, and then for a meat analog we rehydrate prior to use. That are your TVPs that you're using at home. These extruded proteins, these porous, dry, crunchy particles that you can rehydrate in water and then cook in stews or stir fries, etc. Yeah. So two very fundamentally different processes. Yesterday we've seen the high marsh extrusion. Today we're going to see low marsh extrusion. You're going to make TVPs, the classical TVPs. Yeah? Yes?
So for those expansion, so it happens to both starch and protein.
Yes.
So I know for the starch, it melts, the high temperature melts it, and then as it expands, it cools down, so it'll kind of like hold that shape. So for protein, was it the same? The protein was kind of melted so it can expand?
Yeah, so the protein is essentially a melt. You get a protein melt. And then like with the starch, actually, so in some sense it can even trap maybe the steam even a little bit better because it's very surface active, as we know from a protein. So it's a very effective foaming agent. So it expands, it typically expands a bit more leathery type of lamella. You will see that today. And then when it cools down, it actually becomes glassy. The other thing with proteins, we briefly discussed that, there are some covalent bonds formed at high temperatures. What are these bonds? Disulfide bonds. So starch doesn't cross-link. It just, you just quench it into the glassy state. The protein also quench in the glassy state, but actually when it's in really high temperatures, it can start forming some of these disulfide bonds. So you cross-link that protein structure. And then you have that, basically it's irreversible. We talked about it yesterday. If you rehydrate your TVPs, they stay intact. You can cook them for a pretty long time. They still stay more or less intact. If you would cook up a, let's say, starchy cereal, it will, or put it even in cold water, it will disintegrate really, really quickly. So the main difference there is that these proteins actually can form covalent bonds, and the starches don't do that. So there's a little bit of a chemical difference there. But from how we process this, the process is actually for low moisture extrusion for cereals and for TVPs are really similar. Yeah, the underlying chemistry is a little bit different. Yeah, does it answer your question?
Thank you.
Good. Okay, recap. So are we ready for some hardcore engineering? No, just kidding. We'll keep it the basics. So we discussed this diagram. I'll just quickly go over it. Low moisture extrusion, we hydrate, we heat up a lot. So we soften, then we start to cross-link, we expand. In the reaction zone we have the cross-linking, and then upon cutting, it starts to cool down. So we extrude, expand, we cut it. It starts to cool down and lose water. So actually we go back to almost the initial state in this diagram, but of course we have transformed, we have converted this ingredient into an actual product. High moisture extrusion, we really hydrate it, heating it up, then we extrude at somewhat lower temperatures, but also here the softening zone and reaction zone are at somewhat lower temperatures. Then we extrude it in that cooling die. That cooling die is really contained, so we have very little water evaporation. We typically, if you extrude at a water content of 50%, if you determine the water content after extrusion, typically we find something around 48%, plus or minus a few percent. So we lose very, very little water. Then we cool down to room temperature and we have a hydrated product. And you've seen that all yesterday. That's a really leathery structure. It's, this is, as you will see today, it's really hard and brittle. This is really a leathery structure with a lot of water. Yeah, that's also an application makes a lot of differences. Because let us then go to an overview of the properties of the so the low moisture meat analogs, high moisture meat analogs. I maybe could have even put here TVPs. So where are they different? So water content, of course, is different. I think this is actually, I would say, if after extrusion they're even lower, I would say around 10%. This is actually when the water content during extrusion. The extrusion temperature is typically way higher for these low moisture meat analogs. We need to bring them in that reaction zone, which is at higher temperatures, but also want to have enough driving force for that steam to evaporate. So we want to get that expansion, and the higher the temperature, that really works better. I was just working a few weeks ago with one of our PhD students working in the cereal technology group, and he was really, you have to put that extruder close to, feels you're approaching a limit, which is true, but you really have to go down in water content, you have to go up in temperature, and at some moment you will see you start to form these very thin lamella, and you get really nice expansion. So you go to pretty extreme conditions. High moisture extrusion is somewhat lower temperatures. Then we talked about the differences in die. That's really the difference in the setup and the extruder. And then if you know the final product, so this is a pretty dry product. Here you retain that water. And here we have that rubbery, that leathery texture. Here we have the dry, brittle, glassy texture. It's a dehydrated product. So also there, I think in the product applications and the cost of product application, you see a lot of difference. Oh, this is some low moisture stuff. Let me just open that. I think we can pass around a little bit. Okay, they're still not fully dry, but they're drier, yes. I'll just pass on a little bit of this strand here. I can maybe pass it through the room. So basically this is a dehydrated product, and we have consequently way longer shelf life. So these TVPs you can store, for instance, in bags or big bags or in silos. You can keep them for months. So if you, let's say, if you're, let's say, a producer of let's say these plant-based hamburger patties, and even we saw yesterday one of these big companies that contains TVPs. It's really cheaper and more convenient for also for your stock keeping to actually work with TVPs. It's a less critical ingredient. If you have the high moisture meat analogs, you need to store them either refrigerated, but then you have a shelf life of maybe 2 weeks. And in the majority of situations, we actually freeze them. Now, freezing of product is expensive. So if you can get by using TVPs in your product as an ingredient rather than high moisture extrudates, it's way cheaper. So it's one of the reasons that in these hamburger patties we still use TVPs. It's just from the whole economics works out way better. Yeah, and also, you know, there's not even the transport. TVPs weigh, you know, very little. You transport a lot of air, but it doesn't weigh anything. If you transport high moisture meat analogs, you transport a lot of water. So there are very many reasons that actually, you know, if you are in product development and you really have to look at your cost effectiveness, you want to see a really key consumer benefit in using a high moisture meat analog. It really needs to be a key factor, because otherwise it's always going to be way more expensive than using a TVP. Yeah? And also, and there's another factor why TVPs are still used, is just the scale of production. I mentioned to you yesterday that visit I made to a pet food factory, and of course it's a cereal-based product, but just with the single screw extruders we can produce tons and tons per hour. We can just keep on running the whole thing. With low moisture extrusion, even though we scale it now to some extent, production scale is still way smaller than of low moisture extrudates. So if you want to use them in a product, you can use these as is. These ones, either in product development, if you want to make that patty in a company and then sell the, you know, ship and sell the patties, you have to rehydrate it, or if you're a consumer at home, you have to rehydrate before use. Yeah, these use as is. And then where you apply them, meat extenders, they're a great application there in ground beef or so. You can add some of that. You actually don't know. You hardly notice it. In some sense, if you do it well, it even improves the some of the sensory characteristics of especially lean ground beef. You know, beefs get usually texturally better if you have some fat. We typically go really lean these days. Adding some of these meat extenders can actually make, you know, help retain some moisture, make it a little bit more appealing to eat. And they're used a lot in ground meat analogs. I mentioned the patties. Think also about things like sausages, etc., etc. Yeah, and here typically their use is restricted to whole, and actually they use them in nuggets as well. Then whole meat, you know, actually the high moisture meat analogs where we use them, that's actually in the whole meat type of thing. If we want to show there's a chunky piece of meat, and actually if you see the fiber texture, ideally upon eating we can even experience some of this fiber texture. And that can include things like pulled pork type of things, you know, where pull things, but typically it's, or we slice it. But that's where we really use these whole meat products, where it should really also from the eating experience and from the visual appearance, you know, look like something which is cut from a meat muscle rather than being ground. Yeah. So these are the reasons. Many of these reasons coming together that's the reason why that low moisture meat analogs, these TVPs, are still so incredibly dominant in the field, and I think they're going to stay. Good. So we go back to the extrusion process, and as we've already seen, there are a lot of potential parameters that we can start influencing, or that we can monitor. So if you look at extrusion, and please recall also that extrusion setup upstairs from yesterday. So there are things that we can adjust ourselves. You know, we can just turn a knob, program a number, set a temperature. So the thing that we can really easily vary is the screw speed. We have that fully under our control. Yeah. We can set the barrel temperature. Yeah, we can have a number of these segments. You can program them. You can control the feed rate of your product. You can either feed very little or you can feed more. There's of course a maximum to it. If you feed too much, the extruder can't take it with it. But within that limit, it's up on you. You can control that. Then you also can control the water feed rate. This is with the pump. You can either prehydrate your ingredient or precondition them, control how much water is in there, and then you can inject some water. And you can also control that. You can program that. How much of the water are you injecting in the barrel? It's all your, that's your call. You get the shots there. And then also one thing which is really also an independent variable. In the end, it's you who decide what you're extruding. You decide, I'm going to use a pure pea protein isolate as we did yesterday. I'm going to mix it with a starch, or I'm going to make, what's very popular in the field now, protein blends and so on. And any additives you want to use. I usually think that we can do a lot without additives. I think it's more on the physical control of your materials and your process engineering. We can do a lot without additives, but additives certainly have a key role. But I see a lot of people just, it sticks, let's put something in it to avoid stickiness. So you can do a lot with additives and that. That's all your call. Seems to be pretty good. 5 parameters we can play with, and I don't want to talk with the students here. With experimental design, we can make it really pretty complex if you want, already with these 5 parameters. Yeah, so there's a lot of trials that we just would throw them all in. But then we have dependent variables. These are things that result from the extrusion process. We can't control them directly. We can only control them indirectly. And how do we do that? If we want to control, it means that we know what we want to do. Let's say we want to increase the pressure or want to decrease the pressure. You can't program a pressure. Say, I don't want to have my die pressure at whatever 43 bars. It would be really cool if we could, but we can't. Or for maybe low moisture meat analog, I want to have it at 6 bars. Still, you need to control the pressure. Yeah, you need to control the pressure. Yeah. So if you want to be able to control the pressure, it's you need to understand your extrusion process. You need to understand what's going on in that extruder barrel, in conjunction with the die, that results in the pressure. And you can't predict it in an absolute manner, but you have a feeling, if I increase the water content or decrease the water content or increase the screw speed or decrease the screw speed, what is the effect on that pressure? So that's where, and actually if I'm training students on our extruder, so I train them to be operating themselves. The moment that I say, yes, you know what you're doing, you can run it by yourselves, is they have an intuitive grasp of these feedback loops. You need to be able, or one needs to be able to say, okay, a pressure ramps up, I need to do ABC. Yeah, that's for your product quality. It's also for safety, because you can at some moments you can get runaway pressure. And I've actually run extrusion processes where pressure goes up way beyond 250 bars, which is a lot of pressure. There's more than the gas in these flasks that you have in the lab. They max out about 200 bars, I think. So if you're not careful, you can just ramp up, especially low moisture processes, you can really ramp it up to way beyond the standard for the extruder. Usually there's some kind of safety thing in there, but be careful. So it's for your safety first and foremost, but then secondly, you want to be able to control that pressure to be able to control your product quality. Yes?
Can the extruder blow up?
Yes.
And blow up and hurt the people around it? Or
Oh yes, absolutely. You can get seriously hurt. I must say I've never been in a situation that someone got hurt. Now I'm looking at Dr. Hassan there.
I just want to make sure that that whole liability. California have a high liability.
Yes. I'll take my flight back straight after my talk. But yeah, so actually, if you don't take, I remember once at Cal Poly we were running. Actually, there was we were interested in high moisture extrusion, and there was some kind of old homemade cooling die. So let's give it a try. And Dr. Amin here starts to remembers what it is. It was really, I don't think it was some kind of home-made thing. I thought, let's give it a try. So we're running it, and then actually that was not a very well-designed cooling die, so that pressure went up to 250 bars. So then we shut it off, but in that Klextra extruder, the barrel segments are, they're long, basically, you shift them on long metal rods and then you bolt it together. So these are 10 elements, each of 10 centimeters, which are really bolted together. And we actually, at that pressure, some of these the flanges between these elements, they would set, they would move a little bit, and actually the product would shoot out at the side. Yeah, just a little bit, but it happens. So I know where I think they're pretty well designed extruders, but that's about the limit from what you can do with them. I once was running for a company. I was still based in Europe for it was a big US food company running trials in their plant. It was single screw extrusion. It was some kind of pasta analog we're extruding. And then they were starting, and I actually had told them the water content on, I have to think, on wet basis, and they thought it was on dry basis. So they started with a really wrong water content, and before they went, they even didn't ask. They were just at 8 o'clock on a Monday morning. We had 11 tons of legume flour in the storage area for 5 days of trials, and they were starting. And I think at 8:15. They didn't blow up the extruder, but they blew up a very important part of the extruder. So that was the shortest. We still stayed around for a couple of days. We could do a couple of things, but we couldn't do the trials. Yeah, and it's just because of the misinterpretation of the water content. I had calculated on one basis, without this. We had no prior discussion. We just came in. We're starting the extruders, and then bang, there it went. So yes, you can damage extruders. You can also, and I have certainly not seen any significant issues around extrusion with personal people getting harmed. But be always careful. It's hot, under pressure, with power, with everything. So really be careful. Yeah, and if the pressure goes up, shut down. If you don't control it. But for that reason, so for safety reasons first, and then secondly to control product parameters, the purpose of extrusion training is not only to know how to program the thing and how to build it together, but also get a feeling from the feedback loops in the extruder. Yeah, we'll probably do some scenarios. So pressure, product temperature, also really critical. It's not an independent parameter. It results from what we do here. The shear rate, that's actually targeted to the screw speed. That's the easiest one, so we can actually control it over the screw speed. The viscosity of the melt, that's a material property. And the reason, I mentioned that blowing up of the single screw extruder in Germany, with that trial with 11 tons of flour, there was a viscosity issue. If you have a way lower water content than you're planning to, the viscosity is way too high. Yeah, so viscosity of the melt you can't control over the water content and temperature. Then a parameter, we spend today time on that, the specific mechanical energy. That's the parameter I want you to really know. Because this is the thing which is really important in monitoring extrusion processes, and is I would say the broadest accepted parameter that we use in extrusion scaling. Yeah? And then the last one, it's a bit surprising, maybe residence time. Actually, residence time of the product in the extruder is a little bit of a... It was for me, when I initially started to actually reflect about it, a bit unexpected. You said, yeah, I know how much material I'm feeding in per unit time, and I know how much material is coming out. At some moment that's a steady state, it should be a mass balance. You know away from these mass balance equations, you know how long the product stays in the barrel. You just don't know. There's no way that you can, from the extrusion trial yourself, can derive that. Yeah, you have to do specific analysis to actually determine that. So it is a result from the whole process, and then the pressure we can read, the product temperature we can read, but for instance, residence time we still don't know. We have to do something special to get the residence time. Basically, what you do if you extrude, you steady state, you put a little bit of a dye in it, a colorant, and then you time that, and when the product really starts to change color, you say, oh, this is my residence time. Yeah. It's pretty interesting, but from the engineering equations, the residence time just drops out at some moment, and you don't know unless you set up a way to really measure it. So, independent and dependent parameters. Yeah. And where the actually the dependent parameters, as you see them, are very often the real critical ones. This is not for you to keep, learn by heart. So this is the way I typically go about in designing extrusion experiments and in actually capturing some of the data. Now, if you run the extruder like the Thermo Fisher one here, that 11 millimeter one, it will capture the data for you. So you can say, oh, good to go. But still, I must recommend that you plan this. I think, Bilal, are we sharing this sheet out to course participants?
Yes.
Okay,
yes.
Good. So this is actually a way that we set it up. So here you can actually you have one adapter for your extruder probably
yes.
now. This is for our extruder at this is the bray bender we have in Minnesota. So we have two feeders. We have the water pump which you calibrate. Of course, you indicate what you're doing here. This is actually a screenshot from a training that I've given for a couple of collaborators at the time with Bilal apparently here, and one of our grad students. Then here you can actually program. You can actually say, hey, you can start designing your series, for instance, with the temperatures over your extruder barrel. Yeah, you say, okay, I want to start zone 140. This is where you feed your product. Second zone, want to go to 80. So we want to heat it up. We want to denature the proteins. Then we go to 110, 110, 110 apparently here. So we apparently will want to get that product temperature to 110 for the first experiment. So then we see, oh, this is all constant here. So this was clearly not a trial series where we're varying the temperature. But then actually during the run, we're taking the experiments, and this looks suspiciously, actually this extruder is pretty accurate. So actually we get usually the temperature that we set it up in steady state. So these are the recorded temperatures from the experiments. Then we have here the pressure. That's actually not in bar. I think that's in PSI, which we now can convert. So this is PSI. So we have here the die plate pressure is pretty constant during our trials. And then we have here the feed rate. We set it at 3 kilograms an hour of one ingredient. Then the water pump speed, which gives us the pump rate for the water. And here is also constant. Here increase it a little bit. And then, so here actually have the sort of solid feed. Here we have the water injection. So then we calculate from that already on the go the water content. So we know during the trial already, oh yeah, we're aiming at that 50% water content of 50%, and actually we're maintaining it. Here we increase the water feed rate a little bit. We see that the water content goes up a little bit. Yeah. So you design your experimental series, then you capture the data when you go, and you keep an eye on the parameters as they go, and even calculate some things which you want to know. Is that water content still 50%? These type of things. And then what we varied here in this series, finally at the bottom here, so actually here we did a screw speed sweep, as I call it. So we increase, we start with 100 RPM, you go to 150, 200, 250, 300. So we say, okay, let's vary this one parameter, which is screw speed, and then have a look. We collect the products, and we also see we can calculate here some further parameters. This is where we're going to, the torque and the SME. We see here variation specifically of that specific mechanical energy. I will come to that parameter. So we vary the screw speed. We see that one of these dependent variables varies in a systematic manner. So that was the purpose of this trial, to collect samples as a function of the screw speed. All other parameters constant. So collect sample and monitor this, dependent parameter, this specific mechanical energy. This is also and this is a trick when I actually worked in the pilot plant where I was doing trials for one of my clients at the time when I was in Switzerland, in the Bühler pilot plant in eastern Switzerland, which is a beautiful pilot plant. Great extrusion engineers. This is a trick I learned from one of those. Because you're going to sample. So a lot of things going on. You know, you collect your data, you run your extruder, you have your feeder. Usually there were two people running an extruder. So you're going to collect samples. Now, instead of writing down all these parameters on, let's say, your Ziplocs, the trick they employed at Bühler, and I think it was a great one, I'm always doing it, I say, just record the time. You know, 11:43, 11:51, 11:57, 11:59. So actually the screw speed sweep you can do pretty quickly, small extruder stabilizes quickly. So we've been actually sampling here pretty regularly to get these samples. And if you go, you collect your sample, write down the time, you know, and then notice here, you have all your parameters here. So you have your sample and you have your process data. Yeah? And that allows always to easily find them back. Because you won't, you won't be in a situation that you have a beautiful series of data, a beautiful series of sample, and you don't know which sample is related to which process condition. So that's one of the tricks, and since I learned it, I'm always using it, and I'm training everybody. Collect the data in that manner, and then use the time to identify the samples. And at the end of the day, you can actually, put a label on it with more details or so, but you really have that bookkeeping, during the trial. And during the trial, you're always under time pressure. Always something happens, always more to be done than you're almost able to handle. Yeah? And then I've added some conditions. If we work with the cutter, we can program that here, but we didn't do it. But here with high moisture extrusion, so you also record here some of the parameters related to that cooling die. Yeah. So we'll be sharing this sheet. If you're doing extrusion trial, it's really useful to work with that and keep track of what you're doing, collect your data, and also really be able to connect your time point here to your actual sample. So you can do that later on the real analysis, because you can analyze all kinds of properties on these extruded materials. Like yesterday we did the swelling analysis, we did the anisotropy, today we'll do texture analysis, and it's for this sample. Yeah? Good, any questions on this? Let's go on. So how do we start? So you have seen it a little bit in the various phases during the trials yesterday. So typically we first start, and then if you heat your extruder, make sure it's thoroughly heated. Not when the thing just says, hey, I'm at the right temperature. I usually give it another 20 minutes or even more, especially for a bigger extruder. A bigger extruder can even take more time to really thoroughly heat up there's a lot of steel that needs to be at temperature. Then usually start the screw speed, low screw speed, and then start feeding a little bit of water into the barrel. No solid yet. Feed water just a little bit, starts flowing. Make sure that the water flows in the right direction. So if you tend to have backflow because it's very runny, increase screw speed a little bit. And don't inject too much water, just a little bit to keep that, that you don't hear metal on metal, but it's just lubricate a little bit. And then, of course, you don't wait too long. You see some water coming out of your barrel, out of your die. Stepwise increase the solid content. Start feeding some solid material in your barrel, and then increase that. And then you can also adjust, either increase, usually decrease the water content until your set value. So in a couple of steps, you increase your solid feed. You start building some cohesion, some mass, some viscosity in that material. And then you can actually get it to the solid content or the water content that you want to be. If you're happy with these conditions, really great. But always you can do some fine tuning if you're not fully happy with that. Let's say that the base level texture or products properties. You can fine tune a very sensitive parameter, which you can change really easily. Is the water content. So you can always fine tune a little bit. To say, is this the texture, is this the structure that I want to have? It's very sensitive to water content. And then if you do trial series, I will always advocate to do some systematic variation in some of these independent parameters. I know also some of other professors or other people, they recommend doing experimental design where you do the statistical analysis, you have some sparse matrix with these type of things. I think that's good for a second run. I would first explore the properties of the material by really varying some of these independent parameters. The easiest to do, and it was on that previous screen, is that screw speed sweep. You have it stabilized at, let's say, fairly reasonable screw speed, and then you can stepwise increase that or decrease that. Yeah, it's really easy. Just, I'm now at 100 RPM, let's do it 200 RPM. Well, let's say 300 RPM. Really easy. It gives a lot of information, and particularly gives some information, as you see later on that SME parameter, the specific mechanical energy. Then can you do also variation in die temperatures, or even temperatures in your barrel. Thing is that's slower before it sets. And very typically also say from low to high, that's usually the way I go about, because heating that die or some of these extruder barrel segments is way quicker than cooling it. Actually our extruder for the low moisture die should have actually a separate whole cooling system, oil-based cooling system that we don't have. So actually heating it up is like that. Cooling it can take really time because there's, we do it now by forced air. We just blow air through the cooling mantle there, but it comes down really slowly. So it really when you overshoot your temperature, someone can go take a coffee, take lunch, come back and try it again, because it's really, you heat up really quickly. The cooling down very often is somewhat slower, or sometimes very much slower. So if you want to do a temperature set from low to high, again, you can play with that. And then also, and that's actually where the samples you have seen yesterday, but it's a variation of water content. I always work with the roles of water in foods, all kinds of different roles: physical stability, chemical reactions, plasticizing, crystallization, but also viscosity. The variation of water content will give you dramatic change of the viscosity of your protein mass and have an instantaneous impact on about any parameter within a minute or so. So one example, I mentioned pressure goes up. Let's say I'm running my extruder, I see a pressure at the die plate going up, I start to be worried a little bit. I want that pressure to come down. What can I do? Well, something really easy that I can do, and we'll see result within a minute. Huh? Increase the water content. Yes. So it's really effective to really get the pressure down really quickly. Is increase the water content. If you see it running up, increase the water content. Pressure comes down again. Yeah. So that's fine tuning here, and here actually maybe even as a safety measure of water is really, really useful. And then, of course, if you do a trial series, then also, especially in research, R&D, you very often want to run multiple blends and blend compositions. Yeah. Now, that's typically something you have to plan very diligently, especially if you're one feeder. Because, you're running that feeder. The thing is, you don't want to stop your extrusion, then empty out that feeder, clean it, put in a new one, and restart. Because you can maybe do 1 or 2 trials a day. That's not very much. So do all these easy parameters before you start thinking about that. Because here it's typically, this is the if you have one feeder, that's where you actually are. It's really tricky to manage the changeover. The way with one feeder I would usually do it. You have that feeder, so run it down. Usually there's a safety level. Actually, our current one has a very high level safety level. So I'm empty. No, you have still a lot of stuff. So we overrule that security the whole time. Run it down. until it's almost done, which still is quite some material. Then you can put in your new material, but then still it will take some time before you flush out all that mixed material and you get your pure new blend composition. So with one feeder, it just is very cumbersome to change over from one blend to another one. But still you want to do it. Very often you want to explore. You know, you have a protein, you want to blend it with another protein. You don't know which levels it is. I think Abe was here yesterday talking about his research, looking at the amount of, I think, almond meal during extrusion. So you want to test it at different levels. And especially with bigger extruders, there's a lot of material in that feeder. So here you want to plan that very, very carefully. Yeah? There's also a reason why I wanted to have 2 feeders with our extruder. Because you can load one feeder, let's say, with one blend composition and already have the second one ready with the other one. It's seconds and you switch over. Switch the feeder in it, so you can within 5-10 minutes you're running with your fully new blend. Then if you have enough, you're enough staffing around, someone can clean that first feeder and maybe load with the third blend. Yeah, so that's a way why 2 feeders are actually convenient, because especially if you want to run a lot of compositional variations, a lot of variations in how you mix things together, 2 feeders are really good. If you have gravimetric feeders, you can even do that on a quantitative basis by just feeding the 2 in different ratios. You can run them at the same time. And then basically on the screen, and actually that sheet that I have here is adapted for it. We have actually, this is for our 2 feeders. You can actually you can program the series with 2 feeders, and then you see actually the composition of these ingredients coming out. So with 2 feeders, you can just feed them at the same time and actually get a seamless transition in by just pressing buttons on your control screen and doing it. These Buehler pilot plants actually had 3 feeders which you could use, which was amazing. We never used more than 2, but I got completely hooked upon it, and I could convince my colleagues to invest another 35,000 for actually the second gravimetric feeder. And it's actually very, very functional. Yeah? So then sampling, then take samples when the parameters are stabilized and then record the time and usually the extrusion parameters in that sheet. The sheet is not essential, but it gives you typically enough information to start to do your initial data analysis. Modern extruders record it all in their storage. They store the whole process data on their internal storage. You can get it either over your internet link or with a USB stick. You can get that data, but you get massive amounts of data. You have to really big files, it samples every second or something like that. You get massive amounts of data, and so there's a lot of work. So I rather have a simple extrusion sheet because it basically gives me what I need for 80-90% of my purposes. I don't even need to go back to what is stored on the computer at the extruder. Way simpler. I like to keep it simple as well. Way simpler to get a good way ahead by just recording some of these parameters. But you have your whole profile stored and you can analyze all the data. Make sure that the internal clock of your extruder is set to the right time, because then you can correlate it back to that extrusion sheet and to the samples that you have. Because that 11:51 here, if your internal clock on your extruder is, let's say, 3:41 p.m., you can't link it back to your process data. So that's another reason actually to keep this sheet, but also make sure that the internal clock of your extruder is at the same time, because you can link everything back to your samples. Yeah? And then shut down. Who likes cleaning extruders? Yeah? Especially Bilal likes cleaning extruders.
Someone has to do it.
Not if you do the shutdown in the right manner. It's way less work. Because one way you can shut down is just say, oh, I have my sample, let's, there's some big red button, slam it, the whole thing freezes up, So you can just stop it, or you can just really go down. The thing is, then you have to dismount the barrel. You have to, we have a clamshell, so it's easy to get it still out. But otherwise you have, or to pull out your screws if they're all that gluey, that gooey stuff around. It's pretty of a thing, and then you have to scrub everything off. Yeah, not very appealing. Still happens sometimes if you have just to shut down the trial because of unforeseen. Typically, what I do is the reverse of what you do here. But so gradually decrease your solid feed, increase your water feed. Yeah, so you're going to make it more liquidy, more liquidy. There is a limit to it. The thing is, upon starting up, you're increasing the viscosity because you increase solid feed. You decrease the water feed. So what happens with the viscosity? Goes up. Yes, I see someone pointing up a finger. Goes up. So if it's more viscosity, then the screws have more grip on the material. You can push it more actively through the extruder. Yeah. So you can build up pressure. So you can force things out of the extruder. You need to have the grip to force it out of the extruder. Now we have something which is quite viscous, and we're going to decrease the solid content. We're increasing the water content. What happens with the viscosity? Goes down, becomes more runny. What happens with the grip of these extruder screws on that more and more runny material? Goes down. So if you shut down, if you then so lower the solid content, increase the water content, the extruder will have some more issues to get that stuff moving. You can do it, but I love the phase because you have to play a little bit with extruder. Then sometimes say, let's increase the screw speed a little bit or increase a little bit more. You try to get, in some steps, you have to be very careful. You can actually get all that solid material out of your barrel, and at some moment you run it again with clean water, almost clean water. Then you can shut it down, cool down the whole, your whole barrel, make sure that really the pressure is gone. And then if you take your screws out, you will see your screws are 80% clean. So way less work to clean it. Huh, Bilal, is that true?
I was not listening.
Not listening, oh my gosh. Good, not listening.
I'm trying to set up the afternoon session.
Good.
Give me one more chance.
One more chance. I will test your presence in 10 minutes. So the thing is, if you ramp at water content, let's say if you do low moisture extrusion here at 160 degrees centigrade, also make sure that your temperature goes down. Now what happens if I put a lot of water at 160 degrees suddenly? What happens? Going to be a lot of steam.
That's what we trained in 1921.
1921?
Trains in 1921. That's steam.
Oh,
steam
yes,
trains.
yes, steam trains, yes, yes. You don't want to be near anywhere where you have a huge blowout of hot steam. That's really scalding. So typically if you do that, especially with these low moisture trials where the temperature is high, also reduce the temperature, start reducing the temperature there so that you really keep around 100. They're okay, it's still really hot, but it doesn't come out like a spout of really hot steam. Yeah? So this is basically how I go about and running my trials, and at the end the extruders are typically quite clean, so easy. Cleaning is way, way, way easier. Yeah? And especially for bigger extruders, it matters a lot, for the cleaning. Good. I think we have 20 minutes, so I'll just smash through all the engineering. We'll see where we end up, where we don't need to finish everything. So let's see, we go to the engineering aspects. So let's build a screw together. Yeah? So the first thing. We have here all these elements around the screw. We discussed it yesterday, transport elements, kneading blocks. We have here, I included that for today, a reverse transport element. Why would we need, it's not a question, it's just, we'll get to it. Why would we need a reverse transport? We want to get it out of the extruder. We don't get it sent back normally. Still, we use very often reverse transport elements. So these ones actively transported in the right direction. This one is going to send the material back. There's a very important purpose for it. And then we have these dispersive mixing rings that were actually below us. Can we inject the flavor? Yes, in that extruder barrel. Just before we We extrude it into whatever, low moisture, high moisture extrusion die. We can inject an oil in here, or better even an emulsion. And then with these mixing rings, we can actually disperse that in the mouth. These are actually dispersive mixing elements. Yeah?
Can I ask, like,
Yes.
so where is the reverse element placed?
We're going to place it. Yeah, we're going to build a screw. I will. Yeah, we'll do it in the simulation. Huh? So let's build a screw together, and I have to see if I can do that on the Mac. Oh, sorry, on the PC. I usually do that on the Mac. So we have here a barrel, as far as I could design it in PowerPoint, with here a shaft. So all these elements are mounted on a shaft. So here we have the feet opening. This is the rotation direction, and this is twin screw. But we'll just, you design one screw, but the other screw is really the same one. Then we have some ports that we can use, and here we actually have the die. Yeah, we can mount a low moisture extrusion die. We can mount a high moisture extrusion die. Yeah. So doesn't matter too much. Let's do a profile for high moisture extrusion. Yeah. So we feed our material here. Yeah. What do we first need to do? Convey. We really need to get it out of the way as quickly as possible. So which element would you choose to get it out of the way as quickly as possible? Large pitch. Great. So let me see. Now I have to see if I can do that on. Oops, no, this is the.
That look good. We'll take that one.
Yes. Yeah, I have actually. Oh, what is happening here? Up. Oh, we're back. Security warning. Let me see. Let's do it here. I think you can do that. So we take one element here. Do we need more elements of that? So do a couple of more. Control. What was it? Control C and Control V. Good. So we do a couple of those. Shall we do some more of those?
It's really simple. I mean, I bought it. It seems like making the shish kebab. Just
Yes.
putting things, the skewer.
Yes. So yes, it is.
Lucien, you also have it in Armenia, I believe.
Yes, you have them with a lot of flavors. Let's see if we can do it again. A Control V. I used Macs until 15 years ago, and I really have unlearned how to use a Mac. So sorry, PCs. So how many of these do we? Are we more, or do we want to have more, or not? One more. Good.
We can decide.
Yes, you can design. So what do we want to do? So we feed here. We start to transport it in. Is this screw segment, is it really full? Depends a bit how much we feed, but typically we see stuff coming, the particles falling down, immediately taken away. Get them out of the way from that opening. So usually there's not so much material there. Yeah? So we want to actually start filling it a little bit. But we still want to transport. So what element would we use now? Small pitch, yes. So let's get a Control C, Control V. Oh yeah, I'm getting really good at this. Shall we do a couple of those? So we start to transport that material, but with a smaller pitch. So we actually, what we'll see, we start packing that material a little bit more. It's still not fully packed. We transport slower. It also has a bit of time there to start heating up because we want to heat it up. We want to denature and soften the protein. Now we have a port here. So let's say we have a protein. It comes in at a water content of 50%. We want to bring it to 50%. What should we do? Add water. Where are we adding the water? We have ports where we can do. Which port do we want to start adding the water? Do you want to add the water here or here or here?
First one.
Why the first one?
So that it can Hydration.
Exactly, you're on the hydration. We need to really, yeah, I love that. That's really key. Yeah, because the temperature, so you start heating up, but it's still, you don't want to inject water where it's already way over 100 degrees centigrade. So here it's maybe 60 or 70 degrees centigrade, so we can easily have the water in. And we need to hydrate. So hydration, especially in small extruders, is a bit of an issue because it's really short time, a short, part of the extruder where we really can do that hydration. So let's put in a port there. So Control C, Control V. Oops, not in the screw. So we can put here an injection port for water. Yeah? What do we do afterwards? Mixing? Kneading. Let's say the softening temperature of my protein is that the water content is 80 to 90 degrees centigrade, or 90 to 100 degrees centigrade. We're here at 60 to 70. So
Keep moving.
Keep moving, yes. And especially also for starches, because if starches are not, if you have the starch granules, these are little nasty, little hard, little balls. Yeah? You really need to gelatinize them and then they become soft and gooey. Now extruder can handle even, that hard material, but basically it's also not good for your extruder just to run, almost abrasive material in that barrel. So, for these materials, both for starch and proteins, you first want to really soften them up. You want to gelatinize your starches, denature and soften your proteins. So you want to really get to a temperature of 80, 90, 100 degrees centigrade before we start really kneading. We're not yet here, so we keep on transporting it. So I think I'll do another Control V, I think. Oh, no, that's the wrong one. Let's put this away. So we have to do the small pitch conveying element, Control C, Control V. So we're going to put a couple of these. Shall we do a couple of more? Until we're at the temperature that we should be. So typically we'll have quite a number of these elements. I'll do one or two more. So we keep on heating it up and mixing it and hydrating. And I love that word hydration. Keep that in mind. It's not only heating, it's very much also making sure the water is available for your ingredients. Good. So let's say now we're at 90 degrees centigrade. We're at a water content of 50%. So what can we do there? Kneading. So let's put in some kneading blocks. Yeah? So let's say Control C, Control V. So we put some kneading blocks in here.
You can just do Control V, Control V, Control V.
Control V, Control V, Control V. Okay. Good, we start kneading. Yeah? Are we happy starting kneading? Yeah? Would work. Agree? But I said, that extruder barrel, that might, it starts filling up here a little bit and it comes into a kneading zone. Let's say that kneading zone is not yet fully filled. Is kneading effective if you don't have that fully filled? No. So sure, we can have material. Extrude goes here, it gets, we need it a bit. What can we do to really ensure that we have completely stuffed those kneading blocks with material? Reverse, exactly. So that's where we use the reverse elements for. So then we copy and then Control V. So we can put a reverse element here. Yeah? So the material starts to be transported here, hydrated, heated up. Then in that zone, there is back pressure. So it really helps to fill that kneading zone. You don't want to have too much back pressure because you can't transport it anymore. Yeah, because it will really stay there actually, and suddenly you have blocked your extruder. But for judicious placements of these reverse elements can help you. You might maybe do it a little bit later in extruder barrel. You can experiment a little bit with that. But for some of these kneading zones, it really helps to increase the efficiency of your kneading by including some, here and there a reverse element. Yeah. So back pressure here is high enough to force it then even over that hurdle set by the reverse element. What do we do then? What do we want to ensure? That it moves. Yes. Which element do we use for that? Do we use the big pitch or do we use the small pitch? Small pitch. Yeah. We want to have that steady, going steady on with also that it's really with that small pitch you can have a lot of force. So we can effectively move that through the barrel. So here we have that reverse elements, and then we do a couple of these forward mixing elements. Yeah. So let's do a couple of those. What we then can do, we can mix more. We can knead more. So depending, and that's really where this key decisions, design decisions on your screw profile. How much of those kneading blocks do I need? Yeah. So you make there a balance between the forward movement of your material, the active transport, and the thermal effect, so the gelatinization in itself and the denaturation of softening of respectively the starches and the proteins. But very often we'll decide actually you need more kneading zones. So you have a kneading zone which you can have a number of these blocks, but at some moment there's no active transport in there, and it's even sent back. So you just have a limited zone of them. Then typically you get into a transport zone again. You actually start kneading again. So typically what you do there, you can say I want to have a second series of kneading blocks, so we can build them in here. And you can again decide if you want to have a reverse mixing element to force it through, and then you can actually do again active transport. Is this the right way? No, I don't think so. I think we should have this one. So we can actually actively build that. Yeah? Is that principle clear? How we can build that die? And then here towards the end of the die, for sake of time, I think I'll move on. You really want to make sure you build up that pressure that you can actually discharge, that you can extrude that material. So you don't put your your kneading blocks right before here, because especially not with a reverse mixing element at the side, because it will never get through the die. Yeah? Good. So if you design a die like that, I think you have a fair chance. This is actually something which I designed it here. Of course, you close these ports. Actually, with a twin screw extruder, you can even have low pressure zones. After such a reverse mixing element, the pressure is very low. If you have a zone here, you can actually even do venting. A certain process you want to release already some steam. Pressure is here very low after the reverse mixing element. So actually, you can just open up the barrel. You see just the material going through. Yeah? So this is typically how you can design a screw. And this is the screw that is set up. It actually runs from the right to the left. This is actually the screw that is set up in, and you see a bit of the large flights, then a lot of smaller flights, even smaller flights, kneading zone with reverse element, or without reverse element, kneading zone with reverse element, kneading zone with reverse element, kneading zone without reverse elements, and then here some movement to get it through. With the elements that we have, elements are very expensive. This is I would say, a standard screw design that I built. And students and also our researchers can change it. I must say, I recently had a student I recommended to change it. It was a very low solubility protein, which really had weird extrusion behavior. But overall, I found that for 80–90% of what we do, it's a one-size-fits-all. It's never perfect, but pretty conveniently does the job. Yeah, but you can reconfigure that exactly as you want, and really have special purposes. I recently did some recrystallization trials for a company, co-crystallization trials in extruder for a company. We had a completely different screw design for that because the whole purpose of the trial was different. Yeah? Are you comfortable with maybe helping designing a screw at this stage? Yeah? Good. I think I have 5 minutes.
Sure.
So do all the engineering in 5? No, we don't. We'll stop early on. Let me see if I can just explain the first concept. I'm on slide 15 of 53. Actually, there are some backup slides. So we won't, no, that's not the purpose to go through it. No, it's good to go really, we want to make sure that you get the basic principles. Yeah? So key thing, in extrusion, we start to apply mechanical forces. So it's a thermomechanical process. Yeah? We heat it up, that's the thermal part. And then we have the mechanical forces that we shear it. How do we apply shear? Over these screws. Yeah? What is the fundamental way we're exerting work on that material in the screws? It's by turning the screws. What is the measure for that? The key thing in these torques, if you have this screw, let's say in a viscous mass, if you have to turn your screw, it's going to take an effort. Yeah? Otherwise it doesn't move, or it moves really slowly. So in order to turn that screw, we have to exert a torque. Yeah? Now back to your high school physics. You have to exert a torque. What is a torque?
Force.
Yes, it's a force, but it's also a force defined by a certain length here. A certain arm by which you exert a force. Yeah. If I have let's say a bolt which is really fixed, I want to have a key for that, which you have a little bit of a distance, because my force is a given, because that's how strong I am. The actual torque, the moment I can actually exert on that bolt, is if my key is longer, I can actually exert a larger torque on that screw. I recently saw a picture of a guy was building some kind of whatever, I think installations or so, had to mount it, and these have bolts, have tools like that, because it really exerts some force. So what we do, we exert a torque. The electric motor with the gearbox exerts a torque on that, and this is actually a screw. If you would look at, in that direction, it would come here or go into the plane. So the torque is the force that I'm exerting times the length of that arm. And then we see the dimension. It's Newton, the measure of force, times that arm length, which is d, is distance. So that product we call the torque. Yeah. If I start turning that, yeah, and I think I have a little simulation even of that. Let me see if that works. Oh, security alert. Enable content for this session. Yes. So if I start turning that, so I rotate it over a certain angle, I have done a certain work. That's the rotational work. It's Newton's laws of rotational work. The work is a torque times that angle in radians. Yeah? Newton meters, dimensions, and Newton meters, by the way, is the same as joule. Joule is the measure of energy. So I've done some work on these screws. Now I'm not doing it. If I would have a bolt, I could just do that one angle and I'm done. Now in the extruder, I continue to rotate that. So then I have the power. That's actually the angular, the speed of rotation, the angular velocity. So what I'm doing, and let's see if this works here. Actually, I continue to rotate that with a certain speed, a certain rate by which I rotate that axis. So that's the power, the rotational power. That's the power that I'm exerting on these screws. Yeah? And if I have 2 screws, like in an intermesh twin stick screw, it's just simply twice that torque on the individual screen. So I just have that factor 2. Yeah? So this is the way that I'm exerting that mechanical energy. I think I'll wrap up in a few minutes. That I'm exerting that mechanical energy on the material in the extruder barrel. Yeah? So I rotate these screws. I do the work over rotating these screws. And that energy is what we say dissipated in the material. Yeah, I rotate these screws, the energy is dissipated in that material. If I have a very high viscosity material, does it take a lot of effort to turn these screws, or is it easier to turn them? Huh? Higher. If I have really very pasty material, I need to exert more effort to turn those screws. As a consequence, if I turn these screws in the same manner, I'm actually dissipating more energy. I need more force to turn those screws. Yeah? So over that rotation of the screws, I'm dissipating mechanical energy in the material. Yeah? So the key parameter there, that's the specific mechanical energy, which I also listed on some slides. That's the amount of energy that I'm dissipating per unit time over basically how much material I'm feeding in that amount of time. Yeah? So basically it's the amount of mechanical energy that I'm putting in a certain amount of material. Yeah? Why is this so important? What is that energy doing on that material? It heats up, very good, so it's dissipated. But what's happening with that protein or that starch that I have in that system? We're shearing it. So we're shearing, and that's where we actually, that whole extruder, it's a thermomechanical conversion. We're shearing that material. So we're putting over the screws that energy in, and we're shearing that material. So the specific mechanical energy, that SME, is a key parameter to conveniently quantify how effectively, how much am I shearing, am I mechanically transforming my component. Yeah? So it's a real measure of that, how much shearing am I putting in. And I can really calculate it really easily from my extrusion parameters. If I keep track of that sheet, it actually will calculate for you the SME. So this is a key thing, a key parameter to keep track of, which tells you really easily the total amount of shear I have put in, the total amount of energy to shear my material have in. Yeah? There's one other aspect. So I'm dissipating that energy. Where is it going? What is happening with the temperature? Increases. So typically, yesterday I mentioned already, the extruder barrel is an extruder is very good at shearing over that SME. Extruder is really poor for heat transfer, especially big extruders. You almost don't lose heat. So during that shearing, especially I have a high viscosity material, typically low water content. There's a difference between low and high water content extrusion. Low water content extrusion, I'm generating an enormous amount of heat by the shearing. Effectively, the heat generated only in the startup time, you heat the extruder barrel over these heating elements. At some moment, they all go over to cooling mode because you're just generating massive amounts of heat by shearing that low viscosity material, or that high viscosity material. So that energy, as you shear it, but as a consequence, all these molecules get sheared and they resist that, and actually, as a function of the viscosity, a lot of the heat is dissipated. So your product starts to really heat up. The heating during extrusion, especially low moisture extrusion, is not because you need to preheat your barrel, because otherwise it won't really go. But as soon as you're in extrusion mode, you actually basically you don't heat anymore. You usually cool your extruder barrel, and the cooling is very ineffective. So you're generating a lot of heat during extrusion, really transforming that ingredient, ramping up the temperature in the extruder barrel. Yeah. So you can also, if you plug in some numbers, this is actually a little equation. You see these numbers, you can just read from a sheet. I think for sake of time, and I might actually stop here. Let me just see. I had another calculation here to do. So we can actually, just from the extruder parameters, let's say our extruder maximum 80 Newton meters torque, a load of 9%. So we use the torque is 80 times 9%. Screw speed 400. We can plug in these numbers. The equation was on the previous sheet. Solid feed rate, we can just plug these numbers in and we can actually immediately calculate that SME parameter. Yeah? So this is a key parameter, a derivative parameter, but an essential parameter in controlling the degree of conversion of your ingredients. And the other 47 slides, no, I don't have 47 slides here, but the other slides that I still have is actually go into these engineering aspects for scaling. Because under a number of assumptions which are usually valid for most extruders, if you're, let's say, in the same line of twin screw extruders, each equipment developers usually maintain some characteristic ratios and dimensions in scaling extruder barrels and scaling screws from small to big. And then basically, long story short, we'll share the slides with you in the engineering principles. Long story short, one of the best choices, it's not the perfect choice, one of the best choices for scaling is the specific mechanical energy. So if you keep that as constant as one of the parameters in your scaling it from lab scale to pilot scale to production scale, you have a pretty good idea that, it's one of the things where if you keep that right, you have a pretty good chance to land a product which, if you produce it at production scale, is quite similar to what you produce in your pilot scale. I wouldn't even go to completely lab scale because that really looks still a little bit different. But then you can really scale from pilot scale to a production scale with already a good direction. You can already set up your extrusion process at production scale, pretty close to where you want to be. It's not perfect, but it's the best parameter we typically have in our extrusion field to actually allow scaling of the extruder. I think I'm already over time. I think I will call it here, but I just want to go over some of these basic parameters. Basically, in the rest of the story, I would have detailed that more, but I think I got the essence out of it here. Yeah, any questions?
So if you develop a product like with your desired texture and the SME is lower, does that mean it's more cost effective?
What do you mean with cost effective? Cheaper to make?
Yeah, cheaper to make.
What would be the percentage of energy input during extrusion for the overall cost of your product?
I don't know. I just mean like if you make a product that has a good texture similar to animal meat and it's cheaper, does that mean like consumers can buy it for a more affordable price?
Yes, but then it depends again how much is the cost of the energy, so the electric power that you run. What is the percentage of that cost in actually your overall product? Probably it's only 1% or so. So yes, if it would be if that energy you put in your extruder will be a really significant part of the overall cost price of you producing it, sure. But I think I didn't do the calculation, but I would estimate that probably the electricity cost of running the extruder are 1% or so, or a few percent of the overall cost of actually making it. So I don't think it's the critical. I think you can be pretty free in your product development. It's taking any SME that you want to have. Yeah, it's not something we say let's be a low SME to have a cheaper product. There might be reasons to have a low SME, but they're not related to cost. They're maybe related to some textural characteristics. Yeah, so but it doesn't add too much to the cost. No. Other questions? If not, shall we get a coffee?
Thank you so much.
Yeah?
Yeah, appreciate it. Thank you for your time. Sorry, we have only about 16 minutes for a break, and then we have the next lecture before we move on to our hands-on sessions. And just for the student, extruder is just to simplify it, is a large cooking technology with more advanced and fancy. So you heard Dr. Ubbink talking about protein denaturation, starch gelatinization. It's something that you already, the principles are the same. So how to apply that principles that you learn in food science and bring it to this technology and then make sense to finalize the final, like the quality of the final products. So the point here, align what you already learned in the program for 4 years with the new technology, because technology will always change, but the fundamentals that we teach you, it will never change. Protein will always be denatured, starch will be always gelatinized, flavors always volatile, nothing change. Even the technology changes, still your principles is so important to link it to the technology. And the importance of the extrusion is just growing so fast, especially in California. I think there are more than 12 new companies that are investing in extrusion. By 2027, I know about 12 companies will have extruders, and the demand will be increased for such technology and the talent for such technology. So I hope that helps, and take your break. We have another interesting presentation in 15 minutes. Thank you so much.
I'm really confused.
Great presentation as usual.
Okay, so the whole point of my research